Hi everyone, this session I will be continuing with the rotor design problems. Last session I discussed about squirrel cage rotor design. This session I am going to discuss about slip ring rotor design. People who have missed the last session, kindly check the videos. The link is given in the description. Problem statement. A 90 kilowatt 500 volt 50 hertz 3 phase 8 pole induction motor has a star connected stator winding accommodated in 63 slots with 6 conductors per slot. If the slip ring voltage on open circuit is not exceed to 400 volt, find a suitable rotor winding by estimating number of slot, number of conductor per slot, coil span, slip ring voltage on open circuit, approximate full load current per phase in rotor, efficiency 0.9 and power factor 0.86. See, you have to realize in slip ring induction motor we will have exact 3-phase winding, like stator winding we will get a rotor winding also. So that is the difference between the squirrel cage rotor and the slip ring rotor. In squirrel cage rotor you will get a rotor bars short circuited with the end ring, but in slip ring induction motor you have exact 3-phase winding. Like a stator you will have exact 3-phase winding on the rotor. So like a transformer you got primary winding and secondary winding. Similarly here you will be getting the stator winding and the rotor winding. Now given data, power 90 kilowatt 500 volt, that is VL, line to line voltage only they give. Line voltage is 500 volt. Since it is star connected, convert into that phase voltage. Phase voltage equal to VL by root 3. So we'll get to 288.675. Then frequency is 50 hertz. Then pole is 8 pole. Here I missed. So write P equal to 8. Then 3-phase star connection. Number of stator slot is 63. Then 6 conductors per stator slot. ZSS. Number of conductor per stator slot is 6. Then slip ring voltage on open circuit. So line to line voltage on the rotor side. So line voltage is 400 volt. So star connected normally. So V phase equal to VL by root 3. So you'll get a 230.94. So this is the phase voltage. Then find a suitable rotor winding by estimating number of slot. They are asking us to find the total number of rotor slot, number of conductor per slot, coil span, slip ring voltage on open circuit. Then they are asking us to find out the full load current also, rotor current. Assume efficiency is 0.9, eta 0.9, power factor 0.86. Now we'll solve the problem. First, it is like a stator we have winding on the rotor. So to find out SR value we have to use the formula number of pole, number of phase into Q, that is number of slots per pole per phase. Like a stator we have to use this formula first to decide what are the set available. So number of pole is 8. Number of phase is 3. Number of number of slots per pole per phase will start from 1. So we got 24. Next choice 2 we got 48. Then for third choice we got 72. Just keep it. Now we know the condition for rotor. SS minus SR should not be equal to these values. Already we discussed. Kindly go through the old video. Now SS minus SR. How many number of pole? Pole is 8 pole. So plus or minus 8, plus or minus 16, plus or minus 24, plus or minus 40. Now first 8 plus 1 9. Then 8 minus 1 7. After that 8 plus 2 10. After that 8 minus 2 6. So the difference between stator slot and the rotor slot should not be equal to these values. Now we know the stator slot. How many number of stator slot? SS is 63. Now we will select first rotor slot 24. So 63 minus 24 39 it is coming. The difference is very huge. So we will neglect. We will go to the next one. Next one is 48. So 63 is stator slot that given in the problem statement. 48 is the choice of rotor slot. So 48. So the difference is 15. Keep it. Then third choice you check. 63 minus 72 minus 9. Normally we will select a stator slot more, rotor slot less. So if you see in that second choice is the best one, that is 48, because for 72 rotor slot become more, stator slot become less. Actually you can take this also, but normally we will take more number of stator slot compare with that rotor slot. So we will select the second one. In the second one, what is the rotor slot? 48. If you go with the first one, the difference is very huge. So that is the reason we are going with 48. So number of rotor slot is 48. So we fixed the value. Then T phase. for stator, that is number of turns per phase in the stator. TS or T phase. What is TS or T phase? ZSS into SS by 6. Already we discussed in the stator design. So TS equal to ZSS into SS by 6. ZSS is number of conductor per stator slot. SS is number of stator slot divided by 6. So it is giving 63. Since the slip ring induction motor has stator winding and rotor winding, that equally we can consider it as the transformer. So it is called like a rotating transformer. So the transformation ratio concept we can apply here. In the transformer we will take that is N2 by N1. N2 by N1 equal to V2 by V1 we will take. Similar concept we can apply over here. There N2 is that primary turns. Here we will consider rotor turns TR. N1 become here stator turns. V1 become stator voltage over here. V2 become rotor voltage. So N2 by N1 become TR by TS, V2 by V1 become VR by VS. So from that we can find the total number of turns per phase on the rotor side. So TR equal to VR by VS into TS. So now if you substitute the value, we will get a 50.4. We have to round off the value because it should be integer. Turns should be integer. So we will take a 51. Now we need to find out the rotor conductor per slot. Rotor conductor per slot we have to find out. So what is the formula? 6 TR by SR. So 6 into TR will give total number of conductor. Total number of rotor conductor divided by SR will give conductor per slot. So 6 into 51 divided by 48, 6.375. See here. So I am approximating into 6. Originally it is 6.375, but I can't put a 0.375 conductor. So I am in rounding up to 6 conductor. So there will be a change on the turns. So again we need to find out the TR value. This is corrected TR value. This is theoretical TR value, TR. Now since we taken 6.375 into 6, we have to find the original TR value. So what is the TR? TR is nothing but ZRS into SR divided by 6. So now if you substitute 6 into 48 divided by 6, so it will become 48. So this is the actual value. This is calculated value. This is the actual value after doing this correction. So TR, total number of turns per phase on the rotor, become 48. Then we need to find out the voltage. So again we have to use the same formula. This is for the calculated value. These voltages are the maximum value for the given TR, which TR 50.4. But now we are taking into 40. We adjust into 48. So we need to find out the slip ring voltage. So again we have to use the transformation ratio formula only. TR by TS equal to VR by VS. So VR equal to TR by TS into VS. If we substitute that all the values, original values, then we will be getting 219, approximately 220 volt. This is the phase voltage. But we will check the voltage between two slip rings. So that become line voltage. So voltage between slip ring voltage. Voltage between the two slip ring is what to do? We have to multiply by root 3. So root 3 into VR. So root 3 into 219. So we will get a 380.95 volt. So this is the voltage across the slip ring, line voltage. This is phase voltage, this is line voltage. Now coil span. What is coil span? Total number of rotor slot divided by number of pole. So total number of rotor slot is 48, number of pole is 8. So coil span is 6. Now Q we need to find out. So what is the Q? Kilowatt divided by efficiency into power factor. So if we substitute, we will get the Q value. So from the Q value, we can get that I phase. What is Q? 3 V phase I phase into 10 raised to minus 3. From that, what is I phase? Q divided by 3 V phase into 10 raised to minus 3. Now if we substitute, we will get the I phase value. So from that I phase, we can get the rotor EMF. What is the rotor MMF? Rotor MMF is 85% of stator MMF. That already we discussed in the procedure. Rotor MMF equal to 85% of stator MMF. So what is the rotor MMF formula? IRTR. What is the stator MMF formula? ISTS. So 0.85, 85%. So from that, what is IR? IR equal to 0.85 ISTS divided by TR. Now if you substitute all the value, we will get a 149, approximately 150 ampere on the rotor side. So in the rotor conductors, 150 ampere current will flow. Approximately 150 ampere current will flow. Now only this much is asked in the problem statement. For our curiosity, we will go with, we will continue. Cross sectional area. So from that, how to find the cross sectional area? AR equal to IR by del R. So del we can assume 4 ampere per millimeter square or 5 ampere per millimeter square, like that we can assume. So we can, here I taken 4 ampere per millimeter square, so that I converting into meter square. So I have to multiply by 10 power 6. So 4 into 10 power 6. This is 4 ampere per millimeter square. To convert into meter square, I am multiplying by 10 power 6. So if I put, I will be getting 37.448 into 10 power minus 6 meter square, or 37.448 millimeter square. From that I can find the diameter of the conductor also, like in stator. Okay, so it's up to us, but in the problem statement they asked only up to rotor current per phase. So what and all we got all the things. That is estimating number of slot we got, number of conductor per slot ZSR we got, coil span we got, slip ring voltage on open circuit we got, then full load current IR also we got. If you have any doubt, mail to me.